Today's topic is the mole and molar mass. So get your paper, pencil, and calculator, and we can begin. Now, there are many things that we buy by weight rather than counting out the individual pieces, like coffee beans, or jelly beans, or rice, or any other number of things where it's just impractical to count out each individual piece. Here's an example of counting by weighing. If we have 10 push pins and we know the mass of 10 is 4.7 grams, then we could figure out the average mass of one push pin by dividing 4.7 by 10. So the average mass of one is 0.47 grams. Well, then if we had a pile of push pins and we know that the whole pile weighs 84.6 grams, we could figure out how many push pins are in that pile without having to count them one at a time. We could just take the mass of the pile, 84.6 grams, and divide it by the average mass of one push pin, and we would be able to calculate that there are 180 push pins in the pile. So we can come up with the number of pins without counting them, but by weighing them. So we do the same thing in chemistry. It's not possible to count the individual atoms or molecules because they're too small and there's too many of them in a sample to count them out. But we can determine how many atoms or molecules are present by weighing the sample. So we're going to count molecules and atoms by weighing, not by counting. And to do that, we're going to use the concept of the mole. So the mole is a unit of measurement that contains 6.02 times 10 to the 23rd pieces. So if we're talking about a mole of basketballs, we would have 6.02 times 10 to the 23rd basketballs. Or if we had a mole of pencils, we would have 6.02 times 10 to the 23rd pencils. And if we have a mole of water molecules, we would have 6.02 times 10 to the 23 water molecules. Now, it's not unusual to use a word to represent a specific number because we do it all the time. We use the word pair to represent the number 2. A dozen always represents the number 12. A ream of paper means you have 500 sheets of paper. And if you had a mole of atoms, you would have 6.02 times 10 to the 23rd atoms, because a mole represents that specific number, same way as a dozen represents 12. And 6.02 times 10 to the 23rd is also called Avogadro's number, named after Lorenzo Romano Amadeo Carlo Avogadro. So if we took 6.02 times 10 to the 23rd and took it out as scientific notation, we'd have to move that decimal point 23 places to the right, and the number would look like this, which is a very big number. Let's see, we have 1,000, million, billion, trillion, quadrillion, quintillion. We get to 602 sextillion. That's a really big number. What would that look like if we had that many water molecules? How much water are we talking about? Is that going to be the water in a swimming pool? All the water in the Pacific Ocean? All the water on the Earth? What would 6.02 times 10 to the 23 water molecules look like? Well, you might be surprised to learn that it's really a small amount of water. It's barely more than a sip. It's just 18 milliliters, which is why in chemistry we have to use a number as large as 6.02 times 10 to the 23rd, because our atoms and molecules are so small that we need to have enormous numbers like that in order to have enough sample to really work with it in the lab and do experiments with it and to handle it and to know that it's there. So it's important to remember that a mole of different substances will have different masses in grams. Even though they both will contain 6.02 times 10 to the 23rd pieces, and let's look at it this way. If you have a dozen elephants and a dozen bunny rabbits, they're not going to weigh the same either, even though you have 12 of each, because an elephant is much bigger than a bunny rabbit. And the same idea with atoms and molecules. Atoms have different masses. Different compounds have different masses. Some are heavier than others. So if you have exactly 6.02 times 10 to the 23rd of each of them, they won't weigh the same because the individual pieces don't weigh the same. So the mass of 1 mole of a substance is called its molar mass. And the units are going to be grams per mole because we're talking about the mass of 1 mole or mass per 1 mole. And if we're talking about a mole of an element, it's going to be the atomic mass in grams of that element. And we're going to find the atomic mass on the periodic table. And we're always going to round our atomic masses to the hundredths place. And if we're talking about the molar mass of a compound, we're going to need to find the sum of the atomic masses of all the atoms that make up that compound. So let's try some practice. If we wanted to find the molar mass of carbon, or the mass of 1 mole of carbon, we'd look up carbon on the periodic table. We can see that its atomic mass is 12.011. Well, we're going to round that to the hundredths place. So that last one is going to be cut off. So the mass of 1 mole of carbon would be 12.01 grams. If we were looking for the mass of 1 mole of boron, we'd find boron on the periodic table. Its atomic mass is 10.811. And again, we're going to record it to the hundredths place, so it would be 10.81 grams. When we look up copper on the periodic table, we can see that its atomic mass is 63.546. We're going to cut off that 6, which means the 4 has to round up, and the mass of 1 mole would be 63.55 grams. So now let's try to find the molar mass of a compound like carbon dioxide. If we had 1 mole of carbon dioxide molecules, we would have 1 mole of carbon as well, because the carbon has a subscript of 1 in the compound. So we're going to look up the mass of carbon, 12.01 grams, rounded to the hundredths place. Looking at that formula, we can see that oxygen has a subscript of 2. So if we had 1 mole of carbon dioxide molecules, we actually have 2 moles of oxygen there. So we need to multiply oxygen's atomic mass by 2. So we're going to multiply 2 times 16.00 to get 32.00 grams. And then to find the mass of the whole compound, we would add them together. So the sum is going to be 44.01 grams per mole, and that would be the molar mass of carbon dioxide. Now let's try to find the molar mass of glucose, C6H12O6. So looking at the compound, we see that carbon has a subscript of 6. So we're going to need to multiply the atomic mass of carbon by 6. So it's 6 times 12.01, which would be 72.06 grams. The hydrogen has a subscript of 12. So we're going to multiply hydrogen's atomic mass by 12. So 12 times 1.01 is going to be 12.12. And the oxygen has a subscript of 6. So we're going to multiply oxygen's atomic mass by 6. And 6 times 16 comes out to be 96.00. So to find the molar mass of the compound, we're going to add those together. And we'll see that the sum is 180.18 grams per mole. So now it's your turn to find the molar mass of a compound on your own. I want you to find the molar mass of aluminum hydroxide. The formula is given to you here. Pause the video while you're working, and when you have an answer, start the video up again to check your work. So the aluminum doesn't have a subscript. It's understood to be 1, which means there's only 1 mole of aluminum. And so we're going to take the mass of aluminum off the periodic table, rounded to the hundredths place, 26.98. Now the oxygen has a subscript of 1 inside the parentheses, but there's also a 3 outside the parentheses, which means everything inside this parentheses has to be multiplied by 3. So there's really 3 moles of oxygen, so 3 times 16.00 is going to be 48.00. And again, the hydrogen also is inside the parentheses with a subscript of 1, and it needs to be multiplied by 3 because there's a 3 outside the parentheses. So there's 3 moles of hydrogen. 3 times 1.01 is going to be 3.03. And then we need to add all those together to get the molar mass of the whole compound, and it comes out to be 78.01 grams per mole. So let's try another practice problem on your own. This time you're going to find the molar mass of magnesium acetate using the chemical formula given. Pause the video while you're working, and when you're done, start the video up again to check your work. So looking at this formula, the magnesium does not have a subscript, so it's understood to be 1. So there's only 1 mole of magnesium in the compound. So we're going to look up magnesium's atomic mass, 24.31, rounded to the hundredths place. Well, the carbon has a subscript of 2, and it's inside a parentheses with another subscript of 2 outside. So we're going to multiply these subscripts together, and there's actually 4 moles of carbon. So we're going to multiply the mass of carbon, 12.01, times 4, and we'll get 48.04. Now the hydrogen has a subscript of 3, but there's also a subscript outside the parentheses. We need to multiply the 2 subscripts together. 3 times 6 gives us 6 moles of hydrogen, and we're going to multiply that by the mass of hydrogen off the periodic table. And again, the oxygen is inside the parentheses with a subscript of 2. We need to multiply this subscript by the one outside. 2 times 2 is 4 moles of oxygen. 4 times 16.00 is going to give us 64.00 grams. And again, we're going to add all of those up to get the molar mass of the entire compound, which would be 142.41 grams per mole. Now, for good measure, let's try one more practice problem. I want you to find the molar mass of ammonium sulfate using the chemical formula given. Again, pause the video while you're working, and then once you have an answer, start the video up again to check your work. So let's see how you did. The subscript on the nitrogen is understood to be a 1 because there's no number there. But it's inside the parentheses, and there is a 2 outside the parentheses. So we need to multiply by 2, and now we know we have 2 moles of nitrogen. So we're going to multiply the mass of nitrogen, 14.01, times 2 to get 28.02. Now the hydrogen has a subscript of 4 inside the parentheses, but there's also a 2 outside the parentheses, so we need to multiply both subscripts together, and that's going to give us 8 moles of hydrogen. We're going to multiply 8 by the mass of hydrogen off the periodic table, and that's going to give us 8.08. The sulfur doesn't have a subscript at all, so it's understood to be 1. When we look up sulfur on the periodic table, its mass is 32.06. And the oxygen has a subscript of 4, so there's 4 moles of oxygen. 4 times 16.00 is going to give us 64.00. And again, we need to add them all together to get our total for the compound, and it's 132.16 grams per mole. So you did a great job today. Thank you so much for joining me, and I hope to see you soon.